What we're going to be talking about for this first section, S1, is just some basic power system modeling methods and equations. We like to go through this because this is the guts of what most of simulator does in the background when you're doing any kind of your analysis, your ATC, your power flow, your contingency analysis, and so on. They're all going to be based on your power system modeling methods and equations. So we like to do a review of the security section of these methods and equations before we get into talking about the PV/QV curves and the advanced contingency modeling and things like that. So we'll go through and talk about several topics in this section. We go through and review what the idea of nominal voltage levels are and per unit values. We talk about admittance and impedance, the Y-bus matrix, and where the values for the Y-bus matrix come from your buses and branches, loads, etc. We'll talk about what the power flow equations are. We will talk about what PV, PQ, and a slack bus means for the different types of buses. And then we talk about what we use for the load flow calculation, which is Newton's method. We'll talk about the fact that you can have multiple solutions and what the right solution versus the wrong solution might be. And then we'll see a little example with a 2-bus power flow and talk a little bit more about PV and QV curves and maximum loadability later on. Okay, so starting with nominal voltage levels, it's just a matter of discussing why do transmission systems operate at many different voltage levels. And the reason is that power is equal to voltage times current. So therefore, for a given power, if you use a higher voltage, the current will be lower. Well, why do we care about that? We care about that because of transmission losses, which are a function of the square of the current. So if we can keep the current lower, we can reduce losses. So by transmitting at higher voltage, we have lower losses for the same amount of resistance. So that's why we care about different voltage levels. So for an example, if we want to transmit 460 megawatts at 230 kilovolts, that means it's 2,000 amps. At 115, it's 4,000 amps. So because the current is twice as high for 115, that means the losses would actually be 4 times higher. So that's the importance of the higher voltage levels. The problem with higher voltage is that it tends to be more expensive to build and maintain, so there is a trade-off. And that's why voltage varies depending on the situation. So what you might see in a typical system is something like this, where we have varying nominal voltage across the system. That's great for minimizing losses, but it makes it harder for engineers or anybody to calculate what the flows are on the system when you're dealing with different voltages on different lines all over the place. So what we've done is we use a normalization method called the per unit method to normalize everything to one standard scale to make it a lot easier to do our calculations. So the transmission voltage is normalized using what we call per unit values. It's set up to avoid worrying about the various voltage level transitions created by transformers. It also allows us to compare voltages using a percentage-like number across the system. All buses in the system are assigned a nominal voltage. Normally this corresponds to the physical voltage rating of devices connected to the bus, and the voltages are expected to be close to this. So therefore, in the per unit method, this means that a 1 per unit voltage is usually the normal or nominal value. Strictly speaking, it doesn't have to be. It's just a number used to normalize those various parameters. An example of that is in the western US. There's a lot of 500 kV transmission, but it generally operates at about 525 kilovolts. So you might see the rating of 500, but you might consider normal or nominal to be 525. So that's just an example. So how do we calculate the per unit values? And we do that by using what we call the base values. The power base or S base for the entire system is defined and usually is 100 MVA. There have only been maybe 1 or 2 cases in my experience where there's actually been a real system operating out there that the system model is calculated on a base other than 100. An example is Hawaii, it was 10. So at one time, we had hard-coded the system base of 100 MVA in simulators many, many years ago. And the power company in Hawaii bought our software, and all of their values were off by at least a factor of 10 because they used an MVA of 10 and we used 100. So we modified the software so that they could use or set the system base to 10 MVA, and it would use that system base for everything, and then their models matched up. So typically the system base is 100, and that's common for most of the country, if not the world. The system base is 100 MVA. The voltage base for each part of the system is equal to the nominal voltage of that part of the system. And from these, you can determine the impedance base by calculating the Z base and the I base from the base voltage and the system base. And note that the current base, the I base, does have the square root of 3 in the denominator that comes from the difference between the line to line and the line to neutral. So that does factor in there. So you keep that in mind if you're ever calculating your own per unit bases, that the current base does have the square root of 3 factor in there. And this slide shows why, or where that comes from. So nominal voltages are specified as line to line by tradition. So this is the voltage magnitude difference between the AB, BC, and CA phase. So line to ground voltage is equal to the line to line voltage over the square root of 3. And that's where the square root of 3 then comes into play when you're calculating the current, because the current applies to only one phase, but the power is the sum across all 3 phases. Therefore, you get a factor of the square root of 3 in the calculation for the current base. So here we have an example of voltage base zones. So again, your voltage base zones are separated by transformers. So wherever you have a transformer, you're going from one voltage zone to another. So we've got highlighted here on this slide that we have a voltage base of 345 kV for the top section, 138 kV for the middle, 69 kV for the bottom. That means when you're calculating your Z base and your I base for those sections, they will be different for the top, the middle, and the bottom, because the one factor that's changing in the calculation is this V base value. So determining a per unit value, you simply divide the actual number by the base. So for in this example, we have an impedance of 10 plus J50 ohms with an S base of 100 MVA and a 138 kV base zone. We can calculate the Z base as the voltage base squared divided by the S base, and that gives us a Z base of 190.44 ohms. You take the actual impedance and divide it by that Z base, and you get a value of approximately 0.0525 plus J 0.2625. That is what we consider our per unit impedance for this branch. And in simulator, we expect that when you, for example, define a new line, you insert the impedance as the per unit impedance. We do have some tools that help you put it in and calculate the per unit value for you if you haven't done it externally. But just remember that when you are putting impedance values in simulator, we are expecting that you're putting in the per unit impedance for transmission lines or the per unit admittance, in most cases for things like switch shunts and charging on lines. So the transmission system, now we're going to talk about what the model of the wires looks like. The model of wires in transmission analysis is called the Y-bus, or the admittance matrix. We'll review the various parts of the system and how we model those parts of the transmission system and how you enter those models into the software. So we'll talk about how you would input the values that go into the Y-bus, and we're also going to talk about how you would input other values as well for generation and load and shunts and so on. So the impedance and admittance are related terms of R, X, B, and G. The complex number for impedance is represented by the letter Z. It's a combination of the real and reactive parts of the impedance, so R plus JX. Admittance is the numeric inverse of the impedance and represented by the letter Y. So if you invert R plus JX, you'll get G plus JB for conductance and susceptance. The conversion between impedance and admittance is just represented here on this page. So we're doing an inversion of 1 over Z for the admittance and the G term is a function of R over R squared plus X squared, and the B term is a function of negative X over R squared plus X squared, where R and X are the resistance and the reactance of the impedance. The admittance matrix is used to model all of the transmission lines, transformers, capacitors, etc. These are all considered the passive elements of the system. It's the part of the model that doesn't change for different solution states, and it represents only constant impedances for that particular calculation that you're performing of the model. The Y bus is an n by n matrix, where n is the number of buses in the system, and a software package will calculate the Y bus from the data provided by the user regarding the passive elements of the system. So it's going to be constructed automatically from the transmission line impedances, line shunt admittances, switch shunt admittances, and bus shunt admittances. All of those will be used to construct the Y bus internally by the software. So let's talk about some of the building blocks of the model, and before we go into how they go into the Y bus. The basic building block is the power system bus or node, depending on how you want to refer to it and what type of model you're using. The power system bus has a nominal voltage, usually provided in kV. There can be B and G shunt values and nominal megavars provided with the bus as well. And then the voltage magnitude in per unit is calculated and used as an initial guess in a power flow solution, as well as the voltage angle. So these two values are calculated for most buses, not all. We'll talk about what variations there are to that later on. Converting nominal megawatt and megavar into a per unit admittance. So if we talk about, for example, on the previous slide, we said that B and G shunts are provided in nominal megavar. How you convert that to per unit is if the G and B shunts are given as megawatts or megavars, they represent a constant admittance, G plus JB. If you write this in actual units, the B value, or a B shunt megavar, is equal to V squared nominal times B. If you convert to the per unit values, so you come up with a per unit value of B, which is just the B shunt in megavar divided by the S base, because you're talking about power. So you only have to divide the shunt value by the S base. And typically, the nominal value of the voltage, or the value of the voltage, is the same as the nominal value. So we're talking about the B shunt megavar is V squared nominal times B. So if we convert this to per unit, V nominal over V nominal is just 1. So the voltage actually falls out of the calculation, and you end up with the per unit value is simply the megavar value divided by the S base. So it's a very simple conversion to get the per unit value of a shunt from the nominal value of the shunt. And it's a similar derivation for the G term as well. The values expressed in megawatt and megavars at the nominal voltage for the bus shunts, so we represent a constant impedance or admittance at the bus. The B shunt is represented as an impedance megavar injection. The G shunt is represented as an impedance megawatt absorption. The sign of B and G are opposite for historical reason. G typically represented a load term, and B represented a capacitor term, so that's why the signs are opposite for the G and the B values. The Y bus is affected only on the diagonal element, so only the K column and K row, so this is the diagonal of the n by n matrix for bus K, and only on the diagonal does the G and B shunt factor in, because it is attached directly to the bus at bus K. So the off-diagonal terms of the admittance matrix represent the transfer from bus A to bus B, or bus J to bus K, however you want to look at it. And the shunts don't affect or effectively transfer between two buses. They only inject at a single bus. So they are only diagonal elements in the Y bus. So now let's talk about the model of a transmission line or a branch, and this is true for a line or a transformer. The impedance parameters that are provided are the series resistance and reactance in per unit, and also the shunt charging and shunt conductance, B and G values in per unit. So simulator will expect you to input these values calculated as per unit values when you put in the data. The model that we use is this pi model for the transmission lines. So we have the series element here in the middle, and then the G and B terms are halved and applied to either end of the line as shunt injections. And so note, you don't have to divide the B and G by 2 yourself and put in the B over 2 and the G over 2 values. You're putting in the total values for B and G, and internally simulator will divide those by 2 and apply them to either end when building the Y bus model. The transmission branch effect on the Y bus is to make the Y bus, we express all the impedances of the model as an admittance. So therefore we take the R and X values and we invert them and come up with the G and B values, the admittance values between the two buses, bus K and bus M. And then you end up adding several terms to the Y bus as a result of the transmission line or transformer. We have diagonal elements here and here. And note, in the diagonal elements we have an impact by both the series admittance and the shunt admittance terms on the diagonals. And again, the shunt admittance terms are only included on the diagonals because we put them at the ends of the line where they're connected to the bus. The off-diagonal elements are just the series elements only. And note the difference in sign. It is the opposite of the G and B terms in the off-diagonals. So we add them to the diagonal elements and we subtract them in the off-diagonal elements. For a switch shunt, it's very similar to a bus shunt in terms of how it's modeled and where it goes in the Y bus. You again input the nominal megavar value, which is the megavar supplied by the capacitor at nominal voltage or 1 per unit voltage. It represents a constant impedance, so we use the same conversion as we do with bus shunts. We just divide the nominal value by the S base, and that gives us the nominal impedance, or admittance rather, for the switch shunt. And again, it just affects only the diagonal term of the bus it's attached to. So we take the nominal megavar, divide by the S base, and we add that term to the diagonal of the admittance matrix. So the trend is shunt elements, shunt devices are always going to impact only the diagonal element of the bus they're attached to. Transmission lines and transformers that run between two buses make up the rest of the matrix of the off-diagonal elements. So knowing what we put into a Y bus matrix, what does it look like? This is a graphic representation of a 118 bus system. It's a sparse matrix, which means that it's mostly zeros. So everywhere you see white space in this 118 by 118 matrix is a zero value. We have nothing. It is incident symmetric, which means that if we have a value on this side of the diagonal line, there will be a value on the flip side across this axis as well. The reason it's only incident symmetric is these values do not have to be exactly the same. And in fact, in any transmission system where you have transformers that have phase shifts, they will not be the same because the phase shift is negative on one side of the diagonal and positive on the other. So that's why we call it incident symmetric, meaning there will be a value in the same spot on the flip side of the diagonal, but it doesn't have to be the exact same value. So because we have a sparse matrix like this, we take advantage of that later on using sparse matrix techniques to do much faster calculations than trying to do calculations on a full matrix and having to try and calculate from every single value in the matrix when most of them are zero. There's sparse matrix techniques that let you jump over all the zero values and only do calculations where relevant for the non-zero values. So now we'll talk about how loads are modeled. Loads are modeled as one of three or a combination of three types, which are constant impedance, constant current, or constant power. Most of the time your models are constant power, which means you plug in a megawatt and megavar value and it just stays the same all the time, no matter what's going on in the system. That's represented in the base load model and simulator by only plugging in values for the constant power megawatt and megavar. And it just looks something like this, where you say the total power is the megawatt specified plus J times the megavar specified. And this is the most commonly used form of load in simulator or any load flow model. However, you do have the ability to specify constant current and constant impedance loads as well. Now, if you include a constant current component, what that means is you go back and you look at the equations for complex power and derive the expression for the complex power S, and you'll see that you have S is a function of voltage times the conjugate of the current. So we have voltage and magnitude and angle come into play, along with the specified values for P and Q for constant current. And so therefore load becomes a linear function of the voltage magnitude. So if we look at the complex power equation now for constant current, we now have the magnitude of the voltage multiplied by the current specified, or the power specified. So you would specify a megawatt and megavar value here for constant current. The actual value of power that you would get from this component here would depend on the voltage at the bus. So as the voltage goes up, the value of the load goes up. As the voltage goes down, the value of the load goes down.
Can you give me an example?
Constant impedance load is similar. We derive the equation for complex power now by substituting the fact that the conjugate of the current is equal to the voltage divided by the impedance. So if you do that equation, you now end up with V squared over Z. So if you solve for Z, you end up with V squared over S. And so the S load is V squared over 1, which is the nominal, divided by the impedance that you're specifying as constant impedance. And you end up with a factor of V squared for the complex load for constant impedance. So a constant impedance load is a function of V squared. So similar to the constant current, which is a function of voltage linearly, now we have constant impedance is a function of the voltage squared. So again, as the voltage goes up, the constant impedance load will go up faster than the constant current load would go up, and similarly would go down faster than constant current load would go down. And again, this is just, there are machines out there that have this type of response. Okay, so generators. We model them as a source of real and reactive power. So we are usually supplying the megawatt and megavar output of the generator as input into the load flow model. There are also control features of generator. There's automatic voltage regulation, or what we call AVR. This controls the reactive power output to maintain a specified voltage level at a regulated bus. The regulated bus is often the terminal bus of the generator, but it doesn't have to be. It can be a bus that's located somewhere nearby. Typically, the further away electrically from the generator, the more difficult it is for the generator to regulate voltage, because VARs, just for lack of a better way to put it, they don't travel well. So VARs and voltage regulation tends to be a local phenomenon. Automatic generation control is also a control for generation, which is you can modify the real power output P to balance the load flow or the load equation for an area or zone or whatever the generator is contained in. So it can be on automatic generation control to follow balancing load plus loss plus interchange scheduled for the area that it's contained in. So automatic generation control, and there's different forms of automatic generation control that we can talk about later as well. So the generator megawatt power control input is typically you do need to provide at least a starting megawatt output. You also supply the minimum and maximum megawatt output available for the generator. This is, the minimum and maximum are typically enforced. There is an option to enforce it. You can turn that off for a load flow solution if you want, and let the generator violate its minimum or maximum. Note though that if you're doing any type of optimal power flow for market analysis, whether you have this checked or not, simulator will enforce the megawatt limits absolutely, because otherwise it cannot solve an optimal power flow solution if it has no limits. But typically most people want to enforce the megawatt limits all the time. They don't want these generators going outside what they're rated for. There's also an available for AGC checkbox here. The available for AGC is just that. It lets the generator know that it's available for automatic generation control, so that if you're going through and changing load or changing scheduled interchange for an area and you hit the single solution button, that this generator knows that if it has room to move, it can move to meet the change in demand. Participation factor is another option over here, another setting over here. We will talk about that later when we talk about what participation factor control is. It's one of the types of automatic generation control that you can use in simulator. The generator voltage control features, or AVR, is a megavar output. You typically supply a starting megavar output and a minimum and maximum megavar. You can also use a capability curve, which is more detailed but requires more data. Note that in most cases, most load flow models you get, the capability curves are not supplied. You're just given an absolute minimum and maximum, which means your curve over here would just look like a rectangle. You would have one constant value of maximum Q and a constant value of minimum Q for the entire range of P output for the generator. That's typically not how a generator works. A generator curve typically looks more like this parabolic shape. So that means as you get a higher output of generation megawatts, you typically have more error potentially in the VAR output of the generator if you only provide a constant Q max and Q min. But again, most load flow models typically only have a Q max and Q min provided, so it will look like a rectangular shape. You also provide a voltage set point in per unit, and this voltage set point is what dictates how the generator determines what VAR output to inject into the system in order to maintain that voltage, and you specify where that voltage is to be maintained. So in this example, the regulated bus is 12,831 and its set point voltage is 1 per unit. And the remote regulation percentage tells the generator how much it is allowed to participate in the regulation of the voltage. And where this comes into play is when you have more than one generator controlling the voltage at the same remote bus, then you want to provide with each generator how much it supplies. Typically, a lot of times what you'll see is people just put in 100% for all the generators. Simulator will normalize those numbers and determine how much each generator then supplies. So if you give 3 generators 100% each, simulator internally figures out that what they're really doing is 100 over 300, so they're each providing a third. The other option you could do is set each generator to be 33.333, and that's the same thing. Simulator will take 33.333 divided by 100 and determine that they're each supplying 1/3. It only is going to use the generators that are available. So if you have 3 defined, each supplying 1/3, however, one of them now goes offline, it will take the other 2 and say, well, one is 33.333 and the other one is 33.333. That really means they're each providing half. It does dynamically figure that out as you turn generators on and off. And then this section down here is where you would supply piecewise linear segments that would define a capability curve if you want to do that. So you would say at 0 megawatts, it's minus 160 and 200, for example. And then if you go out to 80 megawatts, it might be minus 80 and 160. So it would just do a kind of a straight line approximation for that part of the curve. And then you could say at 162.5 megawatts, it would be 0, so it would be all here, and 140. So it would be, kind of a funky shaped looking curve, but it would be a little bit more of an approximation of this shape than just providing a single min and max megavar. And simulator, if you do provide these and put them into your model and save it as a simulator PWB file, they are maintained in the file. It's just that other file formats typically don't include the capability curves in their core load flow model. They might have it in another formatted file that you would have to load, but they don't save it with their core format file. And we do save it with, we save everything. In the binary file, if there's a field in here and you save the case, it's saved in the binary file. So we save everything. My guess is probably in most of your just standard load flow models, they're not there. And again, I would imagine that this is something that probably when you start getting into the dynamics, when people who are running dynamic simulations, they're probably more caring about this. But still, it's worth noting that in a load flow model, you have some error out here at the reaches of your max P output of a generator if you're only providing a single Q max and Q min. Okay, so let's talk about power flow equations. This is the heart of all power system analysis, and it's based on Kirchhoff's laws for a power system, which is the sum of the currents at every node has to equal 0. So Pn equals P out. It's all based on what, as electrical engineers we've learned, which is you typically don't store your power, your energy, you use it as you generate it. So as it goes in, it also goes out. So why do we talk about a power flow when we're talking about the sum of currents at every node? Why don't we talk about a current flow? Well, the reason we talk about a power flow is that many loads, like heaters, are just big resistors, which should just be an impedance. So why do we solve a power flow? And the answer is because our input data is typically megawatt and megavar values. Because the experience of utilities for more than 100 years show that consumers behave similar to constant power over the long run. So if the voltage drops on a heater, the power consumption also decreases, but eventually people get cold, turn the heat back up. So the built-in thermostat and control system probably do this automatically, but in the long term, it balances out to most loads appear to be constant power. So if we derive the power flow equations using the Y bus, we write Kirchhoff's current law at every bus as a matrix equation. So we take the admittance matrix times the voltage vector minus the current of the generators plus the current of the loads has to equal 0. But we're studying power systems, so we like to talk about power, not current. So we convert this knowing that constant or complex power is equal to VI conjugate. We can write the I conjugate as the V conjugate times the admittance matrix. So we have the conjugate of these two minus the voltage times the I conjugate of the generators plus voltage times I conjugate of the loads equals 0. Simplifying this down, we get voltage times the admittance matrix minus the complex power of the generators plus the complex power of the loads, which is what we're used to providing, so it greatly simplifies the equations to talk about power instead of current. There's n-1 complex number equations where n is the number of buses in the system. These n-1 complex number equations are written as 2 times n-1 real number equations because we have both the real and the reactive part of the equations, so if we have, complex equations, so we have the real and imaginary part, but we can separate those out into one equation of all of the real parts and one equation of all the imaginary parts and write these equations separately. I'm not going to read through this entire equation, but this is your equation where the first long part here are the transmission lines, transformers, and capacitors. So this is all coming from the admittance matrix. So these are all your admittance matrix values here. And then we include the P and Q values from the generators and the P and Q values from the loads. And that makes up our P and Q equations at every bus. And the total of these equations should be 0 because we want the total coming in and the total going out to be 0. The variables for the power flow equation, there are 4 parameters that describe a bus. There's voltage magnitude, voltage angle, real power injection, and reactive power injection. The objective of the power flow is to determine all 4 of these values. There are 3 types of buses given in a power flow based on what we know and what we're calculating at each bus. And what we know at every bus is 2 of the 4 values, and we're calculating the other 2. So what we call a slack bus, which there's typically only one of these in each electrical island, we know the voltage magnitude and angle are provided. So they are constant, or should be constant, and we solve at that bus for the P and Q injection. At a PV bus, which is typically a generator on AVR control, so a generator is regulating the voltage at this bus, we know that the voltage magnitude is given because the generator is supposed to be holding it constant, and the power injection is given because we have a generator injecting power there. And then we solve for the angle and the reactive power injection required to maintain the voltage. At a PQ bus, it's either a load or a generator that is not on voltage regulation control. In that case, the P and Q are constant, so we know the P and Q injections are constant, and we solve for the voltage, magnitude, and angle necessary to balance that. So those are the three types of buses you're going to see in a power flow, and simulator labels your buses for you so you know if a bus is a slack bus, a PV bus, or a PQ bus. You can see that. Because there are times during a load flow solution when a bus might change from a PV bus to a PQ bus if the generator is regulating voltage but it hits a VAR limit. It goes from being a PV bus to a PQ bus at that state. So there are times when it can change on the fly. Okay, so now let's talk about how a power flow works. The power flow equations are nonlinear, which means we can't directly solve them. Therefore, to solve the nonlinear equations, we have to use an iterative technique. To solve a power flow, Newton's method is normally the best technique, and we use this method by default. There are some other methods out there that you can try to use. You can use a decoupled power flow. Simulator does include a decoupled power flow if you want to try and use a decoupled power flow. It's typically not as accurate as Newton's method, might be a little more forgiving in some situations. There's things like the Gauss-Seidel method, which is a lot more forgiving to your starting conditions. But Gauss-Seidel has a really hard time narrowing in on and being accurate to the actual solution, and it also does not handle negative impedances, which you do actually run into quite frequently in a load flow model, in modeling three-winding transformers, and in modeling series capacitors. And so Gauss-Seidel is not an option in simulator because it does not handle those typical modeling conditions. So since power flow equations are nonlinear, there's cosine and sine terms which make them so. That means we can't find a direct solution, so we have to use this iterative numerical scheme to determine the solution. For power flow equations, variations on Newton's method has been found to be the best technique, and we have agreed with that over years of research. Without going into great detail, Newton's method is discussed in calculus courses. You consider a simple scalar function and write it as a Taylor series, and you end up throwing away the higher order terms and just typically dealing with the low order terms. And we use typically just the first two terms. And what we try to do is find where f of x is 0, which means that the power flow equations sum to 0 because those are the vector or array of functions that we're trying to solve is the power flow equations. So therefore we estimate it with this equation here where we're trying to find the value of x approximated as a starting value of x minus the derivative of the power flow equations with respect to x inverse times the vector or values of the functions at the starting value. So you're trying to approximate the change in values, and you keep iterating that until you get a change in the values below a threshold that you specify. So we iterate because you take an initial guess, use a Newton step to a new guess called x1, then you use x1 to find x2, etc., until the change in value becomes minimal. So let's take, for example, a previous equation where we said let's assume that we're starting with a value or a function of x squared minus 2. So if you take the initial guess as x0 equals 1 and iterate that equation, you end up getting, after the third iteration, a value of 1.41422. And this is the change function here. You can see it's now 6.024 times 10 to the minus 6, so it's very small. So we're going to say this is small enough change that we're going to stop and consider that we're done. The error decreases quite quickly because this has quadratic convergence. F of xk is known as the mismatch function, so that's this function here. The problem is solved when the mismatch is 0. Note it's not 0, 0, but it falls below a threshold that we specify. Typically in simulator you're solving for megawatt flows and megavar flows, so the usual default mismatch that we solve at every bus is 0.1 MVA. We say if the change or the mismatch is less than 0.1 MVA at every bus, then your system is solved. Now, nonlinear equations can have multiple solutions. So if you consider again the previous example of x squared minus 2, there are actually two solutions where x is the square root of 2 or the negative square root of 2. In an iterative scheme, your initial guess determines which solution you converge to. So if you start with an initial guess of -1, you will actually converge to the negative square root of 2, or what we call the low solution. If you consider a nonlinear equation can also have no real solution. If you consider the equation x squared minus lambda, where lambda is an independent parameter, the number of real solutions depends on the value of lambda. If lambda is greater than 0, there are two real solutions. If lambda is equal to 0, there's exactly one solution, that x equals 0. If lambda is less than 0, there are actually no real solutions, because you end up with x squared equals negative lambda, which has no real solution. So your parameter variation can change the number of solutions of the nonlinear system. The convergence characteristics of Newton-Raphson. The global convergence characteristics algorithm are not easy to characterize. The Newton-Raphson algorithm converges quickly, provided the initial guess is close enough to the solution. However, the algorithm doesn't always converge to the closest solution. And some initial guesses are just plain bad. For example, if the derivative is near 0, which we call ill-conditioned, the process may actually diverge and you may find your solution blowing up instead of converging to minima and finding a solution. Okay, so there are definitely issues with the Newton-Raphson solution. It's not absolutely perfect. You will find situations where you try to solve a power flow or any other type of equations using this iterative Newton-Raphson, where depending on where you start, you may not be able to reach an actual solution. Now, extending scalar to vectors and matrices, Newton's method may also be used when you're trying to find a solution where many functions are equal to 0. So if you let your f of x be an n-dimensional function and let x be an n-dimensional vector, as you see here, you can use Newton's method to solve for that as well. The Newton step is still defined the same. It's just now you're using the vectors of functions instead of just a single function. And so now the derivative delta f over delta x is now a matrix, and we refer to this matrix as the Jacobian matrix in load flow. So anytime you talk about a Jacobian matrix, what you're doing is you're taking all of your power equations and taking the derivative of each one by each variable x. Now a lot of these end up perhaps being 0 if the function has no value of that x term, but you will end up with a Jacobian matrix that plugs in here. So you actually are doing an inverse of the Jacobian. And that inverse of the Jacobian is where you do have some matrix techniques that you can take advantage of to speed up that inversion and so on. So solving the power flow equations, again, they're nonlinear with cosine and sine terms. This means we use this iterative technique to solve them. We define F to be the real and reactive power balance equations at every bus. So those are the functions that we define for solving the power flow equations. And X is the vector of the voltages and angles at every bus except the slack bus. We don't include the slack bus because the slack bus is our reference point where we have the voltage and angle specified as constant for a reference for the rest of the system. So to set up the power flow solution, you recall that we divided the real and reactive power equations into two separate equations. So we have the real power equations and the reactive power equations. So therefore our f of x function, we're going to have a real and reactive power equation for every bus. So P1 and Q1, P2, Q2, and so on down to n minus 1. Our x vector is going to be the angle and voltage. And note that we have delta 1 and V1, and the angle is first and the voltage is second for our voltage vector. And that defines then our delta f over delta x, or our Jacobian matrix, where we basically have each section of the matrix for one set of power flow equations. We divide out into 4 different derivatives of the power equations. So we have the derivative of the real power equations with respect to delta and V, and the derivatives of the Q equations with respect to delta and V, and we have that for every bus. So there are n buses, with bus n being the slack bus, okay? So this is how we define the Jacobian. The power flow equations exhibit the same behavior as other nonlinear equations. In theory, there are up to 2 to the n-1 solutions to the power flow equations. Of these, all or none may be real number solutions. In power system analysis, we're normally interested only in the solution that is what we call the high voltage solution for every bus. So if we look at this 2-bus power system example and consider this lossless example where R equals 0, we have theta is the voltage angle at bus 2 over here, and V is the voltage magnitude at bus 2. Bus 1 is our slack bus, so that's our reference. We have our admittance B is minus x over R squared plus x squared, so we're just taking this value and inverting it, and we end up with a per unit value of minus 10 for the admittance on this transmission line. And the P mismatch is the power of the load minus BV sine theta, and the Q mismatch is the Q of the load plus BV cosine theta minus BV squared. So these are our two P mismatch and Q mismatch equations. So these are our power balance equations. We calculate a series of power flow solutions for various load levels. First, we need to determine the following. This is our Jacobian. So we now take each of these two functions and do a derivative of the function, first with respect to theta, then with respect to the voltage. And so we end up with minus BV cosine theta, minus B sine theta, minus BV sine theta, and B cosine theta minus 2BV. So this becomes our Jacobian. Our x vector of voltage and angle, we have theta and V at bus 2. Our functions are, again, our two power balance equations at bus 2. So this is our function vector, this is our x vector of voltage, angle, and magnitude, and this is our Jacobian matrix of these equations derived with respect to both theta and V. So for an initial guess at each load level, we iterate from an initial guess until the solution hopefully converges. We consider a per unit load of 2 per unit and a reactive load of 0, which is the equivalent of a 200 megawatt load since the S base is 100 MVA. If we consider a flat start for the initial guess where we say V0 is 1 and theta 0 is 0, we'll do a calculation for that. Also out of interest, we'll look at, well, what if we say V0 is 0.5 and theta 1 is minus 1, or theta 0 is minus 1. We'll look at that as well. Might be a little hard to see on here. Hopefully you can see it. This is an example that was set up just in Excel where this was modeled to do a nonlinear iterative solution, and it went through several different iterations of solving this. We plugged in up here our starting values: P load 200 megawatts, Q load 0, X per unit 0.1, so that defines our equations here, and our starting value of 1 per unit with 0 radians for our voltage, magnitude, and angle. And what this Excel program has done is gone through and iterate. Starting with this value of magnitude, it goes through an iterative solution solving these equations until we get down here to about the 6th iteration, and it comes up with a magnitude of 0.9789 at an angle of minus 0.2058 or negative 11.79 degrees. And that is our solution point for starting at 1 per unit. So our initial guess was 1 at angle 0. Our actual value that it settled on, and you can see the difference between them was minimizing as it went through additional. In fact, it was pretty close to the actual solution after the 2nd iteration, and it actually settled on the solution at the 3rd iteration. But what would happen if we chose a different starting point? We won't run through these equations here, but it will just show you the result. The result was if we started with 0.5 at minus 1 radian, we actually end up with the voltage going down instead of up. And so what we've done is we've started on the other side of the PV curve on this at this bus, and it's actually converged to a solution, but it's gone to the what we call the low voltage solution. We typically like to avoid this, which is why you will often see in a load flow, you always start out with values near the nominal 1 per unit voltage, because in theory, you should hopefully stay on the high side or the high voltage side of the solution if you start near the nominal value of the bus voltages. This is just an example of region of convergence. Tom ran through and did multiple load flows choosing different starting points and angles for this little example that we've just done. And what it shows you is what the region of convergence is. Basically, anywhere that you pick a starting point in this red parabolic region right in here converges to the high voltage solution. If you start somewhere outside in this yellow region out here, then all bets are off and you either converge to a low voltage solution or you reach a divergence or no solution. So this is just a kind of a neat little example showing you how Newton-Raphson works well if you give it a starting value that is at least somewhere near what the actual solution should be. But as you get further away from what your actual solution is, the greater your chance of reaching a different or low voltage or another minima somewhere else solution not near where you really want to be, or you might diverge altogether and get no solution. So initial guesses in the red region converge to the high voltage solution. Those in the yellow region, which is a much larger region, actually converge to a low voltage solution. That's why we say for a Newton-Raphson iterative solution, your initial guess is important. What this relates to is what we call a PV curve. A PV curve is generated by plotting these two solutions as the real power load is varied with the reactive load and impedance constant. The higher transmission impedance usually decreases the system capacity or maximum load. So note load values below 500 have two solutions, high and low. If you try to put in a load value greater than 500, you actually get no solution. And it's because there's just no way for the power to transfer across that transmission line. You've exceeded what we call maximum power transfer at that point, and you cannot actually solve the load flow for a load value greater than 500 megawatts. Anything less than 500 megawatts, you will get a solution. Note, as you get close to 500 megawatts, you reach the critical value or the nose point of the curve where there is only one solution. And you will find that your load flow stability is very sketchy as you get close to this point. And slight variations in your load flow could cause the load flow to diverge or collapse, you might say. A QV curve also can be generated by plotting these two solutions as the reactive power load is varied with the real load and impedance constant. Again, load values in this case for reactive load less than 250 megavars have two real solutions, both a high and low voltage solution. Any value of megavars greater than 250, you would have no solution, and your critical value is at 250 here, which is your nose point with only one solution. So this is just kind of plotting what your curve would look like if you resolve this set of equations over and over again, varying your starting value of P or your starting value of Q, and you will get curves that look like this. The nose points on the PV and QV curves are critical values. They correspond to points of maximum loadability from a static point of view. Keep that in mind, this is not dynamic, we're talking about static. This only considers these static equations. Other problems can occur long before the power system reaches this point, like lines overheating or system dynamic problems. So those nose points on curves are not absolute failure or divergence points of your load flow solution. There could be other situations where you actually would fail prior to that because of these things here. The critical values depend on the relative allocation between the real and reactive power. In the previous examples, we looked at varying only the real power or only the reactive power. Obviously, if they're both going up, then your critical point may be sooner than if one or the other is going up. So the mathematical characteristics of the critical value is that the power flow Jacobian is singular at that point. A singular matrix is one that has a zero determinant. A generalization of a scalar case is when the derivative is zero. So a singular matrix cannot be inverted, therefore we cannot solve the Newton-Raphson load flow equations because it requires us to invert the Jacobian matrix. So that's why the critical value is a critical point in the load flow process.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular PowerWorld engineer, please feel free to contact that person directly.